Hello there. This is your introduction to physics, and in this chapter we will talk about units and dimensions. Now, in physics or in science, we only talk about quantities that can be measured, and such quantities are called physical quantities. So, any quantity that can be measured is called a physical quantity. And it is only the physical quantities that we'll talk about in physics, or in general we can say science. So to give you an example of a non-physical quantity, you must have sometimes said that you hate something, right? But can you measure that hatred? You cannot, right? So hatred cannot be called a physical quantity. Now, the reason I'm stressing this is that in science or in physics, we deal with quantities that can be measured. But the question still remains as to how can we measure them, right? Let's think of a very fundamental thing, for example, length. So let's say I draw a line which is this long. Now, forget everything you know about scales and I tell you to measure this line. How can you do that? Well, one way is that you define your own standard. For example, you could say that this length, so this is any given length, you take this length, take it as reference and say that I'll call this length as 1 zeta, right? So I've just come up with a unit which is a zeta and I've chosen a length and I'll say that this particular length, I'll call it 1 zeta, right? Now, using this reference, I can see in terms of multiples as to how long this given length is, right? For example, let's say that if I move this length along this line and I find that this length is 5 times the reference length that I have chosen. So if that is the case, I could say that this length is 5 zetas, right? So what we essentially understand from this example is that to measure anything, we first need to set standards, right? And for in case of length, you already know the standard units are centimeters, meters, kilometers, or miles. So now you can understand that these lengths, we ourselves have chosen them as reference so as to be able to measure any given length, right? So when we say that something is 10 meters long, what this means is that that particular length is 10 times the reference that we have chosen to call as 1 meter, right? So this defines the idea of units, which means that to define units, we have set some standards. For example, let's also take the case of weight. You know that weight, or you'll see, to be more specific, mass is measured in kgs, right? Whenever you buy something at the store, you buy it by kgs, right? So how did we come up with the idea of 1 kg? Well, it's simple. We wanted to measure mass, so we took a defined amount of mass and started calling it 1 kg. So if something had 5 times the mass as compared to our standard, then that particular thing would said to have a mass of 5 kg. Right. So that is the idea of units. Let's now briefly discuss fundamental quantities. So now, there are some quantities, some physical quantities that are made up of other physical quantities. Like the simplest example you know is that of speed. You know that speed is equal to distance divided by time, right? So if you think about it, this quantity speed is obtained by dividing distance and time, right? So speed here is not a fundamental quantity. Rather, it is a derived quantity, right? So it has been identified that there are 7 fundamental quantities, and the list of which you can see in front of you, right? So now you might be thinking, how did we decide that these are the quantities which cannot be derived? Well, if you take a closer look, you would also see that these are the quantities which cannot really be defined with the help of any other thing. For example, let's talk about length. Now, we saw how we measured length. Can you think of defining length in terms of any other known quantity? You cannot, right? Similarly, mass or amount of quantity or current, these are quantities which cannot be derived from anything else, right? So we have 7 fundamental quantities, and the units of which are also shown in this table, and you should remember them. These units are the standard units, right? So another thing about these fundamental quantities is that these quantities are in a way very fundamental, by which I mean that we cannot exactly explain what these quantities are, but we know how to measure these quantities and how to use these quantities to create other physical quantities. For example, you can see that we have used 2 physical quantities, which is length and time, to derive a physical quantity which is speed, right? Whereas if you think about it, and this is something you'll have to really think about, it's very difficult to perceive what length really is, right? Well, I'll leave that thought to you. So the essence here is that we have used 2 fundamental quantities to derive another physical quantity, and this quantity, since it is derived from other basic quantities, is not a fundamental quantity, right? So now all the fundamental physical quantities we have, all 7 of them, they are given special symbols. For example, to write a few, mass is given the symbol m, length is given the symbol L, and time is given the symbol T. The entire list is shown right in front of you. So once again, you should try to remember these quantities, and you would see as we move forward, as we encounter more and more physical quantities, we'll keep discussing their dimensions, and it'll start becoming clear to you why we need to understand their dimension, right? So let's talk about a few quantities and see what their dimensions are. Now, for the fundamental quantities, we have already fixed the dimensions, like the mass is m, length is L, time is t. Let's think about speed. So if you want to talk about speed, so speed is distance divided by time. So distance is length and time is t. So the dimension for speed becomes, let me put 3 arrows just to signify that equivalence of dimension. So its dimensions will be L t minus 1. So this is the dimension of speed. So we usually use these square brackets to indicate that these are dimensions. So this is the dimension of speed. In case you know about acceleration, you know that acceleration is change in velocity divided by time, right? So if we wish to define or find out the dimension of acceleration, all we need to do is write down the dimension of change in velocity. Now, change in velocity will have the same dimension as velocity. Well, think about it. If I subtract 5 meters out of 10 meters, what I'm left with is 5 meters, right? So any addition or subtraction will not cause a change in dimension. So this is something I'll explain again. So I'll come to this again. Let me first finish deriving the dimension of acceleration. Now, let's for now just take it as a fact that this change in velocity will have the same dimension as velocity. So, if that is the case, the numerator has the dimension of Lt minus 1 divided by time has the dimension t. So, let's keep them in square brackets. So we find that the dimensions for acceleration would be LT minus 2. Right. So this is the dimension for acceleration. Right. Now coming to the point of addition and subtraction, think about it. If I tell you that I add 5 meters to 3 seconds, does it make any sense? You cannot add length to time, right? Because it does not have any physical interpretation or any meaning, right? So if you add and or subtract two quantities, it makes sense if and only if the two quantities have the same physical dimension, right? So to give you an example, let me write an equation. So let's say x plus y is equal to a into b. So this is any general equation, but just by looking at this equation, what I can certainly say is that x must have the same dimension as y, right? Because then and only then I can add x to y. Also, if on adding x and y, I am getting a quantity which is a into b, then a into b, the whole product must have the same dimensions as x, which has the same dimensions as y. To see this in an example, remember the first equation of motion is v is equal to u plus a into t. Now, in this equation, you are multiplying, you're adding rather u to this term which is a into t. Now we just said that such an addition is meaningful if and only if both of them have the same dimension. So let's check for it. The speed you know is measured in meter per second or kilometer per hour. Acceleration is measured in meter per second square. So this a into t is meter per second square into second, making it meter per second, right? So you can see the unit becomes the same, right? Also, you can check the same thing dimensionally. Acceleration is LT minus 2. If I multiply acceleration with time, what I basically get is LT minus 1, which is the dimension of speed. And that is why this equation is meaningful and consistent, because the two terms which are being added have the same dimension. If they did not have the same dimension, there was no meaning in adding those two quantities, right? So, comparing these two equations, I hope the logic has become clear to you that whenever I see an equation like this, I can directly claim that x must have the same dimension as y, and both of them individually have the same dimension as that of this product of a and b. So let's now take an example to understand this further. Let's take the example of work. Now work, you know, is force into distance. Now in case you don't know this, don't worry, we'll study this when we get to the chapter of work. Right now, we're discussing this just to understand dimensions and units, right? So work done is defined as force applied into distance. Now let's look at the units of work as well as the dimensions of work. So if we talk about units, then force, you can derive that also. Force, you know, from the second law of motion is mass into acceleration, right? Now the unit for mass is kg, and the unit for acceleration, we just talked about it, is meter per second square, right? So the units for force become kg, meter per second square, right? And the units for distance, you already know, is meters, right? So if we talk about units of work, it becomes kg, meter per second square into meters. So the unit of work becomes kg, meter square per second square. Right? Similarly, if you were to talk about its dimensions, then its dimensions would be the dimension of force. Let's find out from this expression. The dimension for mass is m. That of acceleration we had seen is Lt minus 2, since its distance per unit, which is speed, further divided by time, which makes it distance per second square, or rather meter per second square. Right? So this is the unit dimension for force, making it mLt minus 2. So the dimension for force is mLt minus 2. The dimensions for distance are obviously L. So you get the expression that it is mL square T minus 2. Right? So this is how we can derive the dimensions of any physical quantity. Now, we could discuss a lot of physical quantities, as you would certainly find in your books. But rather than going into quantities that you don't know about yet, we will keep discussing them as and when we encounter them. For now, we understand that units are defined for a way to measure these quantities, and these dimensions are defined because they help us identify that for any physical quantities, what are the fundamental quantities that are used to build that quantity. For example, when we derive this dimension for work, we can see that work is a derived physical quantity, and it is derived from mass, length, and time. Right? So for now, I'll not stress this any further. Rather, we'll keep discussing them as and when we encounter more physical quantities. Right. So now let's move on to error analysis. Now, once again, this is something that we will discuss in more details when we go to experimental physics. The reason is this requires a better understanding of mathematics, which you will get during this course. So once you get that knowledge, it makes a lot more sense for us to discuss it then, but I'll give you a brief overview. So while discussing this, I'm assuming that you have very basic knowledge of calculus, right? So let's say that you have a quantity, let's say distance, which is equal to speed into time, right? So you're trying to measure the distance covered as product of the speed and time. Now say you know that there is some error in measurement of speed and there is some error in measurement of time. So how do you estimate the error in measurement of distance? Now to do that, what we'll basically do is differentiate this quantity on both sides. So if we do that, you can see we'll be able to write that ds is equal to v dt plus dv into t, right? I'm using the product rule, right? Now, in the next step, you divide these two equations. So you basically get that ds by s is equal to v dt plus dv into t upon v into t, right? So now we can rearrange it into an expression that you will see in your books, which is ds by s is equal to dt by t plus dv by v, right? So to generalize this expression, what I can say is if there is any quantity x which is a product of y and z, then the error in measurement of x is such that delta x by x is equal to delta y by y plus delta z by z, right? Or you can, if you strictly want to talk about the error, then delta x is equal to delta y by y plus delta z by z into the quantity x itself, right? And this quantity delta y by y or delta z by z can be called the fractional errors. So delta y by y is the fractional error in y, and delta z by z is fractional error in z, right? So similarly, if you had a case where, say, on the other hand, if you had a case like v is equal to s divided by t, if this was the case, then once again on differentiation you'd get something like dv is equal to tds minus s dt upon t square, right? So once again, if you divide these two quantities, you get something like dv by v is equal to ds tds minus s dt upon s into t. So which can be written as, this will become, the t cancels out, so ds by s minus dt by t. Now, at this point, there's an important thing to note. Even though this expression tells us to subtract these two errors, we know that if there's an error, it will only add to other errors, right? So the result that you'll get will not be a difference, but rather an addition, right? So always remember this, that in case of errors, once you get an expression like this, you never subtract errors, right? They'll always get added. So any fractional error is sum of all the fractional errors for all the quantities that are there. So to make a more general expression, let's say if we had a quantity, let's say y, which was equal to a raised to m into b raised to n divided by c raised to n, then, and I want you to derive this by yourself, you would see that when you differentiate this dy by y, so I'm writing the expression which is after differentiation and dividing, you can see that when you differentiate a raised to m, you'll have an expression of the form m into a raised to power m minus 1, right? And this a raised to power m minus 1 will later get divided by a raised to m, once again leaving with the u with 1 by a, right? So check this yourself, you'll get an expression of the form m into dA by a plus n into dB by b. Now, by differentiation, what you'll get is minus of, so let's take another term, let's call this O. So it'll be O into dC by c, right? But you know that errors are not to be subtracted but to be added. So this is the general expression for error analysis, that fractional error will be equal to the index of power into the fractional error of that quantity, right? So this expression you need not remember if you remember the logic behind this, but this is the expression that is used to find out, or rather do, the error analysis for any physical quantity. So let's now take an example. Let's say I tell you that for a capacitor, now let me briefly tell you what a capacitor is. A capacitor is a device which can be used to store charge. So it is given to you that charge on a capacitor is given by the expression that Q, the charge, is equal to the capacitance of the capacitor into the potential difference across the two ends of a capacitor. right? So you don't have to focus on the capacitor. What you have to focus on is the expression for charge. It is given to you that the capacitance of this capacitor is 20 microfarad with an error of 0.1 microfarad. So this plus minus 0.1 indicates that this measurement has an error of 0.1 microfarad. Now, I'm sure you're aware that micro means 10 raised to power minus 6, right? Similarly, milli means 10 raised to power minus 3. Kilo is 10 raised to power 3 and mega is 10 raised to power 6. So these are some of the powers that you should remember, because we'll often use these prefixes, so to say. So let me show you the entire list of these prefixes on your screen. You can see that this is the list of prefixes that we use to indicate the power of 10, right? For example, if someone says that something is measured in nano, it means it is 10 raised to power minus 9. So nanometer would mean 10 raised to power minus 9 meters, right? So I advise you to remember this list. These are the symbols that are very often used, right? So moving ahead, coming back to this problem, it is also given that the potential difference applied is equal to 10 volts with an error of 0.5 volts. So once again, the potential difference is measured to be 10 volts, but there's an error of 0.5 volts. Now, first of all, for example, if you're talking about voltage, voltage is measured using an instrument which is called voltmeter. We'll study about it when we go to the chapter of electricity. Now, there we'll also study the construction of a voltmeter. So when any instrument is constructed, due to its construction, there can be some errors in measurement, right? So this error probably is due to that construction, that the instrument is such that it can only measure with a precision of 0.5 volts. If we think of a simpler example, let's look at the scale you commonly use. Now, in your scale, what you have is centimeters mark, right? So you have centimeters, and between them, there are divisions to indicate millimeters, right? So let's say this is, say, 4 centimeter and this is 5 centimeters. So now we need to make 10 equal divisions, right? We need 10 equal intervals to split a centimeter into, so we get millimeters, right? So let me not draw all of these, but let's say these are 3 consecutive divisions, right? So let's say this is 4.5, 6 and 7. Now, if you are measuring something using this scale, so this is your normal scale, that centimeter scale that you have, which has 1 to 15, right? So this is between the 4 centimeter mark and the 5 centimeter mark, and between them that there are divisions. So this is, let's say the measurement made is between these two, that is 4.5 and 4.6. So you cannot really say if it is 4.5 centimeters or 4.6 centimeters, right? It could be 4 centimeters, 4.5 centimeters or 4.6. It is somewhere in between. So we can say that the maximum error that can creep into your measurement when you're using the scale is of 0.1 centimeter, right? Because the possibility is that the measurement was very close to 6, but you took it as 5, or it was very close to 5 and you took it as 6. So the only error that can come is after the decimal, right? So that is why this scale has an error of 0.1 centimeter, right? Which is equivalent to 1 millimeter. So the scale that you use commonly has the accuracy up to, or rather has the error of maximum of 1 millimeter, right? So as we move forward, we'll see the reasons of these errors. So for now, let's just say once again that there are reasons for which sometimes errors creep into your observations. Right. So now we know the capacitance, we know the voltage, we are given the expression to find out the charge on capacitor. Now, in such situation, when you're given data with errors, you're supposed to report your answer with the error that can be there, right? So in this case, first of all, we can simply find that charge will be equal to 20 microfarad into 10 volts, which will give you 200 microcoulomb. The unit of charge is coulomb, and you would later study that farad into volt will give you coulomb, right? So that is not the thing to focus on. The first thing that we have done is found out charge by using the expression that we were given. But this result that we have obtained is prone to errors because the quantities that we use to find out this charge themselves have some error in them, right? So now you see that this is a product, right? Remember, we just studied that in such an expression, we could say that dq by q is equal to dc by c plus dv by v, right? Now, this dq can be called a small change in charge, right? Which can also be approximated as the error in charge. So the error in charge divided by the charge itself is equal to the error in capacitance, which is 0.1 divided by 20 plus 0.5 divided by 10, right? So notice that even though capacitance was in microfarad, I only wrote 0.1. This is because you would have gotten 10 raised to power minus 6 in the numerator and 10 raised to power minus 6 in the denominator, right? If we were to be precise about it, right? So further, we've already found out that charge is 200 microcoulomb. So let's take this quantity and multiply on the right hand side. Now again, notice that if I take the charge as to be 200, if I substitute the value as 200, then since I have substituted the value in microcoulomb, the error I'll get will once again be in microcoulomb. So if instead I was to take into 10 raised to power minus 6, by doing that I'll be converting it into coulomb. So if I did that, then the final error that I'll get will be in coulomb itself. So for now, let's not take this minus 6 and see what's the answer we get. So let's leave this expression as such. This is 0.1 by 20 plus 0.5 by 10. So you can see when you take this 200 on the right hand side, 200 by 20 leaves you with a 10. So that makes the first term 1. For the second term, 200 by 10 leaves you with 20. 20 into 5 gives you 10. 20 into 0.5 gives you 10, which makes it 11. Now, since I substituted this value, keeping it in microcoulomb, the error that I've obtained is once again in microcoulomb. So the small change in charge, so it is more appropriate to denote it with delta Q, right? Right, so the error in charge is 11 microcoulomb. So once I get this, what I can say is that the charge on capacitor Q is equal to 200 plus minus 11 microcoulomb. So this is the complete expression for the charge on capacitor, because this tells you that the charge is 200, but there's an error of 11 microcoulomb, which means that this charge could be from 189 microcoulomb up to 211 microcoulomb. So this is what this value indicates, that you can have, the charge can have any value between 189 microcoulomb and 211 microcoulomb, right? So that is what the error of 11 signifies, that this is the amount by which it can deviate from the value of 200. I hope you understood that 189 is obtained by subtracting 11 from 200. Right. So this completes our analysis for errors. As I told you before, if you want to study this chapter in detail, right at the very beginning, then you can refer to our chapter Experimental Physics and you'll get further details of this chapter. As for the introduction, I'll now be moving on to significant digits. Right. So once again, this is something that you'll start understanding as you solve more problems. But let's talk about it. So significant digits means the number of digits which are significant in any measurement, right? For example, if I was to write that I have 0016 apples, right? Then I might as well say that I have 16 apples, right? And this is true for any measurement. So what this basically tells us is that all the zeros which are to the left of any number are not significant, right? So if we were to count the number of significant digits, we'll say the number of significant digits is only 2, which is 16. On the other hand, if the measurement was 1600, then the zeros are on the right and this time they will be significant, right? So in this case, the number of significant figures is 4, right? Now, if you have something written in the power form, for example, if you have a measurement which is 1.67 into 10 raised to power 5, then the number of significant digits is only 3. So this raised to the power 5 is not counted as significant digits, right? So whatever is the power to 10, if we write it in this exponent form, the number of digits is only the digits which are written in the number in front. Right. So now the thing that you should be careful about is that if you have a value of 1600 and if you were to turn this into the exponent form, then it should be written as 1.600 into 10 raised to power 3. The reason is it indicates that your value is definite up to the third decimal, right? Because if you write it 1.6 into 10 raised to power 3, you only have 2 significant digits. It means you do not know about the second place. Whereas from the original, we can see that we have information up to the third decimal. So the zeros which are on the right are significant. So let's now see how to use significant digits. But before we do that, let's see a few basic principles about rounding off a number. I'm sure you already know this. So let's say if you have a number which is 44.236 and I tell you to round this off to the second decimal place. Then in that case, since the number following the second decimal place is greater than 5, since the number is greater than 5, we will increase the previous digit by a value of 1. That is, when you round this number off, you'll round it off to 44.24. So we are basically talking about rounding up a number, right? On the other hand, if the number was 44.233, in this case, the number at the third decimal place is less than 5. Since this is less than 5, we'll round this off to 44.23, right? So if the number is greater than 5, you raise it by 1. If it is less than 5, you keep it as such. But if the number is 5 itself, for example, if you have 44.235, then if this 5 is followed by a 0, let's say if this is the number, then you have to look at the digit before it. Now since this number is odd, this 3 is odd, we will round it off to 44.24. Whereas if this number had it been 44.2250, then it would have been rounded off to 44.22. So since we have an even number, that is why we'll keep it as such, but if you have an odd number, then you'll increase it by 1. And in case there is nothing following that 5, for example, our original example, let's say it is 44.235, so there is nothing after 5. In such a case, we'll keep the number as such. So if the number was 44.235, it will be rounded off to 44.23, and if it was 44.225, it will still be rounded off to 44.22. So these are the basic rules of rounding off a number. I'm sure you're already aware of these things. So moving on to operations based on significant digits. Let's say you have a length L1 which is 25.341 meters. And you have another length L2 which is 31.21 meters. You have to find L3 which is a sum of L1 and L2. Now, doing this is easy. You already know to find L3, you should simply add these numbers which is 24.341 and 31.21. So this will give you 56.551. Now, the problem here is that the values that we have used, for example, L2 only has 4 significant digits, right? After decimal, we only have significant digits only up to the second place. But in our answer, we have the decimal going up to the third digit. So, in such a case, you have to round it off to the second decimal. You have to make it 56.55. The reason being that your answer cannot have more decimal places with significant digits than the values that you used to obtain that answer, right? So since in this case L2 only had 2 values, your answer can only have up to the significant digits up to the second place of decimal. Let's say we are multiplying two numbers 1.2 and let's say 36.72, and this gives us, so if you multiply these two numbers, you'll get something like 46 or 44.064. So once again, in this case, what you see is this has 2 significant digits, this has 4 significant digits, whereas your answer, it has 5 significant digits. Now, as I just mentioned, that your answer cannot have more significant digits than the minimum of the values that you use to obtain that answer, right? So I say minimum of because here you have 2 significant digits and you have 4 significant digits here. So minimum of these two is 2. Hence, your answer should be reported up to only 2 significant digits, which means this 44.064 should be rounded off and reported only as 44. Right. So this was about significant digits. We have so far discussed about units, dimensions, the idea behind units and dimensions. Then we briefly discussed the prefixes that are commonly used, moving on to significant digits and how to round off numbers. Now, this is a brief introduction. From the next lecture, we'll start from our main topics. Thank you.